Hi everyone, my name is Francisco, and in this video I am going to present Flexagon, a collaboration between researchers from the University of Murcia, NVIDIA, and the Georgia Institute of Technology. Sparsity in matrices is an emerging trend in modern DNN workloads, ranging from 0.5% to 90% among a large number of DNNs from different domains. Exploiting this sparsity is done via the sparse-sparse matrix multiplication operation, which may be executed by using three data flows, known as inner product, outer product, and Gustafson's. Current accelerator with support for SPM operation optimize their design for a single data flow. So, which accelerator is the best? Which data flow is the best? Well, as we demonstrate in this paper, that depends on the specific DNN layer. To fill this gap, in this paper we present Flexagon, a creative accelerator that is for first time designed to efficiently execute the SPM operation using the three data flows. This way, the accelerator can adapt to the data flow that best fits each DNN layer. Do you want to know more about our Flexagon accelerator? Then attend our session 4C on March 28 in Vancouver, Canada. I am really looking forward to seeing you all there. Thank you very much.
Hi, I'm Tolua. I'm excited to share with you our work on dynamically tiling sparse computations. Our focus is in a tensor world where a lot of tensors are sparse. Let's consider a specific kernel, matrix-matrix multiplication. Unlike its dense counterpart, which is limited by compute resources, when both operands are sparse, this kernel is memory-bound. On a roofline plot, we want to move up and to the right. We propose doing this by improving data reuse or temporal locality. Static tiling, commonly used in a dense world, doesn't work well due to irregular sparsity. A 2x2 tile may only have one non-zero present, wasting buffer space and at times leading to worse locality and more DRAM traffic than the untiled case. We need a way to make the most of our on-chip buffer, despite the fact that each tile may have different occupancies. So what if we try tiling dynamically? Here we build time-varying tiles, which in the worst case requires an expensive search across a tensor to figure out how many non-zeros it has for a tile. On top of this, we have to coordinate this search across other tensors. In the case of matrix multiplication, the k-coordinates need to match. We call this co-tiling. In our talk, I'll be describing our tiling algorithm, DRT, that overcomes these challenges, is implementable in hardware, and can be applied to a number of prior art accelerators. In fact, our approach, when implemented on a variant of extensor, closes the DRAM traffic gap. If you'd like to find out how we did this, come to session 4C. Hope to see you there.
This talk presents SPADA, accelerating sparse matrix multiplication with adaptive data flow in the session of tensor computation. Sparse matrix multiplication, or sparse stream, is widely used in many scientific and deep learning applications. Sparse stream exhibits drastically varied densities and non-zero distributions. These sparse patterns have different weights on factors affecting the efficiency of the sparse stream. On the other hand, sparse stream can be executed in different data flows like inner product, outer product, and row-based. Each data flow has different impact on the efficiency factors. Therefore, there is high performance improvement potential if we could adopt different data flow schemes with respect to different sparse patterns. To realize such potential, we propose SPADA, which performs adaptive hardware execution according to sparse patterns. First, we propose an adaptive window-based data flow, which is easy to be adjusted and covers wide trade-off space. Second, for the hardware, we propose a mode reconfigurable accelerator, which is efficient to execute the data flow and can swiftly switch among different modes. Last, we propose a profile-guided window shape adaptation algorithm, which can effectively detect sparse patterns in a lightweight way. Compared with SOTA accelerators, SPADA achieves 1.4 times speedup on the wide range of sparse matrices. To find more details, please attend our talk at ASPLOS.
Hello everyone, welcome to our lightning talk, and we are going to give a brief introduction to sparse tier. Sparse operators are commonly used in deep learning, such as graph neural networks and network pruning. But when it comes to deployment, They face challenges in performance and coverage. Performance-wise, mapping irregular sparse operators to parallel architectures and acceleration units can be difficult. Regarding coverage, sparse libraries may not cover all operators used in sparse deep learning. Our solution is a compiler that offers composable abstractions. Inspired by prior work, we designed an intermediate representation with sparse format annotations as first-class members. These annotations can compose sparse computations on various formats, thus resolving the coverage issue. We then enable decomposing the original computation into microkernels, and each operating on submatrix in more hardware-friendly formats, and then map them to hardware units through our multi-stage lowering compilation flow. Sparse-T achieves impressive performance on various benchmarks, notably 1 to 2 times speedup against cuSparse on SPMM, and up to 40 times speedup against sort libraries by kernel fusion. You might be interested in knowing more, so please come to our talk in session 4C and meet us in poster session 2. We are looking forward to further discussions.
Hi everyone, I'm Yaldin. Today I'm going to give you a brief introduction of our recent work, headed Task Mapping Programming Paradigm for Deep Learning Tensor Programs. With the development of deep learning, more interesting applications are getting accessible to the public. For example, we can draw a finger with a simple description, or communicate with a chatbot in our daily language. At each run of these applications, a bunch of tensor programs will be executed. It's expensive to run such applications. For example, it may take about $700K per day to serve the chatbot. To improve the user experience and save the cost, it's very important to develop efficient tensor programs. We can manually develop and optimize tensor programs, but it's usually complex and engineering heavy. Prior works like TVM propose to automatically compile tensor programs, but suffer from suboptimal performance and long tuning time. In this work, we proposed a new programming paradigm based on a concept called task mapping. It gives you best of both sides. It's simple and highly flexible to implement optimizations. We implemented a deep learning compiler called Headed based on this idea and benchmarked it on 5 representative models. Headed achieved lower latency and dramatically reduced the optimization time. If you want to learn more about tensor program compilation and optimization, come to hear our talk on March 28. You can also visit our GitHub repo to give it a try. Thank you.
My name is Olivia, and I will be talking about the sparse abstract machine. The current obstacles with sparse tensor algebra over its dense counterpart is mainly attributed to the large input space of computation. For a fully general system, this includes a long tail of expressions and various compression structures. And for that general system to be performant, this also includes performant backends, like handling data flow accelerators. However, current systems are limited to targeting imperative code for von Neumann architectures only. Performance is obtained from backend-specific or optimizing transformations. Furthermore, current sparse tensor algebra accelerators are limited to only a subset of tensor algebra expressions and need to be programmed at a lower level of abstraction, which is hard for an end user to reason about. To address these problems, we introduced the sparse abstract machine to represent sparse tensor algebra for data flow accelerators. Our system enables increased performance for the end user by natively targeting hardware accelerators, and improves the usability of those accelerators by providing an automatic compilation system from high-level languages. We also designed the sparse abstract machine as an LLVM-like compiler intermediate representation that decouples the compiler design from the hardware implementation, which allows for parallel design, iteration, and development. If you're interested in learning more, please come to our talk on Tuesday, March 28th at 10:20 a.m.